Swayam Prabha. Digital India. Educated India.
At the onset, I would like to thank ACM and Neeldhara and the organizers for inviting me here for the second time. And so as she said, I am from IIT Madras. Today and for tomorrow and day after tomorrow, I myself and my friend Prajakta, we will be talking about matchings in particular. And before I start with a specific problem, I would like to motivate the setup of algorithmic game theory, which is the title of this workshop. So at a very high level, one can think of this field as being designing systems which have a good performance and are designed for participants which are strategic. That is, they have their own goals, and these goals may not be necessarily aligned with the designers of the system. So we'll see as we go along what does the design of a system mean. And I would like to say that at any point feel free to raise your hands, interrupt me and say that you don't understand something. So if something is unclear, it is because I am not putting it rightly rather than you not following it. So let's take a very simple example of elections which have recently happened. So elections happen at different levels. They happen at the college level, they happen at the national level and at the state level and so on. And during the election, there are several candidates whom we are interested in electing, or there are several candidates who are contesting for the election, but there is typically expected that there is a one outcome. So we think about different election than the Indian election system, but there is one person whom we want to vote as a leader. But as we know, each one of us has different preferences over who should become the winner or who should win the election, and not only about who should win the election, but if he doesn't win the election, then who should be the next candidate according to us. So there is this system where we want to elect a leader, and as a designer of the system, one would like to clearly specify how people vote or how people give or submit their preferences. Once the people have submitted their preferences, how are these preferences collated and how is the winner determined? What is the underlying algorithm behind that? This is one example of a system where we would like to design a system where each individual would want to get his or her favorite leader elected into the wherever he is going to go to. A second example is of a government policy decision, and here is where we all of us are taxpayers, we give our money, and the government is interested in taking a place and building some infrastructure there, but the government would want to decide based on the people's preferences what gets built. For example, maybe there is a overbridge that is required. There's another thing that is a park that could be a possibility, or a school that could be a possibility. And again, depending on the needs of individuals and the families, each individual or family would have a different set of preferences. So how does a policy maker or how does the system designer get these preferences from the participants? Finally, once the preferences are collected, how does the system designer get those preferences and decide what the final outcome is going to be? And if the system is not designed well, then there are reasons that people can actually falsify their preferences, saying that although I would like to get this built, I would be able to, if I say this, then it is most likely that the other thing is whatever I like is going to get built, and therefore there are reasons that people would like to falsify their preferences. For example, there was reason in day before yesterday's match that if India lost the match, there were better chances that Pakistan may not go into the match and may not qualify for the semi-finals. So therefore, while losing in general may not be a good idea for the cricket team, but at a particular time losing may be a better option. So therefore, misreporting their preferences or falsifying their preferences may be incentivized if the system is not designed well. So what we are going to do is, these are very high level examples. We are going to look at a very particular example, delve deep into it, and see how the system is designed when everybody is truthful. How does the system behave if some participants are truthful, if a single participant lies and is not truthful, and then if a collection of participants lie or a set of participants lie, can they benefit? So this is the overall theme for today. So to set up our particular problem, I would like to ask, how many of you are not aware of JOSA, the joint seat allocation? Okay, so possibly you have the others are aware of JOSA, is what I understand, the joint seat allocation. So if you are not aware of JOSA, we will describe the system in informal detail. So there are these participants which are these college students. So there are, or sorry, not college students, and these are 12th standard students. And there are these institutes which are offering several programs. So what do I mean by these institute offering programs? Can anybody give an example of what is an institute offering a program? Yes? Yeah, BTech, BSc, we'll think of it for now as BTech programs. But even if I say BTech programs, it's a wide term, so can we be more specific? Yeah, so there are computer science, mechanical, civil engineering, electronics, and so on. But even more specifically, it is at a particular institute, right? So every institute has a certain set of programs. So when we say a program, it is a very specialized thing that we are talking about, which is say, let's say IIT Gandhinagar Computer Science program, then there is IIT Madras Computer Science program, then there is Chennai Mathematical Institute BSc program, and so on. Right? So these are all the programs that we have. And in fact, when you think about JOSA, there are two different kinds of programs which are categorized. One which is the programs which you can enter through via what is called as the IIT, the JEE mains, and the second which is another level of qualification, which is the JEE advanced, right? There are two levels of exams, and there are these two exams have to be given by all the participants. If you are interested in a program which just for which students can get qualified by, or students are admitted using the JEE mains, then you can stop at that. If you want to get admitted into the program where JEE advanced is used, you have to give both the exams, right? So now, given these two exams, students can get different ranks in these exams, or there can be different rank orderings. So think of all of you writing the two exams, and think of there being just two programs for the sake of illustration. So there are two programs, we call it P1 and P2. Right? These are the two programs that we have, and there are, let's say there are several participants. We call them A1, A2, A3, A4. Just for the illustration, we will have 4 participants, right? So now, if you have these 4 participants, each of the 4 participants will have a preference ordering on these two programs. That is, they would like to get admitted into P1, or they would like to get admitted into P2. For this purposes of this lectures, we will assume that everybody who is participating in the system would like to get admitted or get assigned to a program rather than being left unassigned. So we will think of everybody having his or her own preference order, which if I write like this, it means that P1 is a more preferred program for A1 as compared to P2. And many of you who have submitted your JOSA preferences know that you have to rank order this. Even if you have not submitted, it's quite intuitive to say that I like these programs in this order. So this is how every participant is going to order the set of programs available in their preference ordering, right? If there were multiple programs, maybe you are not interested in some of them and you may not rank some of them, right? So so this is the set of programs and this is the set of preferences by the participants. Okay. So also what else do we have in the system? Yes. Qualifications of the students. For example, if A1 is not qualified for the program P1, then there is no point in A1 saying that P1 is my top choice, right? So let's assume that A1 is qualified for both P1 and P2, and for now assume that all A1, A2, A3, A4 are qualified for P1 and P2, right? So they are eligible to write them in their preferences. Still, what else do we have? Yes, somebody else? Yeah, please raise your hand. Number of seats, very good. So we have possibly that P1 has 2 seats because this is a very small system and P2 has just 1 seat. This is very unnatural, but it can happen at some place. So this is a toy example. Yeah, so there are number of seats. Anything else? So instead of talking about the marks of the students, we will say that there is a rank ordering of the students by the way the marks have been assigned, right? So instead of talking about absolute marks, there may be several other factors. So we will talk about a rank ordering of these students. So because we said everybody is able to give all the programs, and therefore we will also say that maybe everybody has listed every P1 and P2 in some order. There are only 2 orders here. So this is how they have listed. Then there is a rank ordering of the students. So maybe this is A2, A1, A3, A4, and there is P2 could have the same order or P2 could have a different order because each program may have in fact conducted its own test and ranked students according to some order. So this could be something like A1, A4, A3 and A2. Right? So this is the input to our system, and these are some things that are known to individuals. That is, each AI or the participant knows his true ordering of preferences. Each institute knows his or its capacity, that is how many students can it accommodate, and it knows its rank ordering based on the exam. It should truthfully reveal that typically, but we'll see why sometimes we may not want to reveal it. Now, what is the goal of the system designer? Yeah. So since you have answered once, I will ask your neighbor. What do you think is the goal of the system designer? All the seats are allocated, okay. Anything else? Yeah, so one goal we can think of is all seats are allocated or good number of seats are allocated. Anything else? Students and institutes should be satisfied as much as possible. Okay, so this is slightly at a very high level and it's not well defined, but I'll write it: students and institutes should be satisfied. Actually, these are programs, but that's fine. So does somebody want to say what does this mean by students and institutes should be satisfied? Yeah, maybe we'll, yeah, if you want to say, I'll give you a chance. But yeah, somebody else who wants to say how will you make it formal in terms of, so if I just say that A1 is assigned to P1, A2 is assigned to P1, A3 is assigned to P2, you have to look at that assignment and say whether it is a good assignment or not. And we have to say that clearly so that anybody should be able to verify that this is a good assignment, and we should be able to design algorithms to output such an assignment. Yes. Okay. Okay, so what she is saying is large number of students should get what is their top choice, and many institutes should get good ranking students according to them, right? So now that we understand the setup, is the setup of the problem clear? So what we are going to do is we are going to make a small assumption that all institutes have what we will say as capacity 1, right? We will just assume for the moment, just to illustrate everything, that all institutes have capacity 1 and all students are qualified for all the programs as well, and they also are interested in joining all the programs. So when you look at a particular problem or instance of this, we call this the instance of the problem. We will say that if there are n applicants and n programs, we will have all n programs listed by n applicants, and vice versa, since they are qualified, all the n applicants are listed in the list in the ranking list of all the programs, right? So instead of having this example which is incomplete, what we will do is take a slightly larger example which is a little illustrative. Yeah. So I am going to write a particular example, which is, we again have 4 participants, A1, A2, A3, A4. And instead of calling them as P's, I will just call them as B's throughout this lecture, and we will follow this convention throughout today. So these are the preference orderings of the participants. That is, A1 thinks the program B2 is its top choice, followed by B4, followed by B1, followed by B3, right? And this is how you have to read out each preference list. Similarly, the programs have also listed out the rankings of the participants. So everybody is okay. So this is what is the input given to us. For now, we will assume that every participant, that is A1 to A4, has this as its true preference ordering, and similarly all the institutes B1 to B4, they have ranked. They have given this ordering, whatever is the ordering according to the marks obtained by the students or whatever was their ranking criteria. Right, so this is what is the input for this problem, and what we want to do, because every program has a capacity of 1, I am not going to write them down, the capacities of these programs. So every program takes one applicant or one student, right? So if people observe this and people are familiar with what are bipartite graphs, there is an underlying bipartite graph where you have students on one side, the programs or the institutes or the B's on the other side, And in fact, this is a complete bipartite graph because every A has an edge to every other B, and in fact each edge has two ranks, one coming from the A side and one coming from the B side. And as soon as we talk about an assignment of students to programs, this is what is called as a matching in the bipartite graph. So just to illustrate, if you had a 3 cross 3 instance, then the graph would look like this, where you had all these edges, and a particular matching would be possibly A1 assigned to B1, A2 assigned to B2, and A3 assigned to B3. Right? This could be a particular matching if it was a 3 cross 3 system. This is a 4 cross 4 system, and there is an underlying bipartite graph which I am not drawing. Right? Okay. So what our goal is to compute a matching or a collection of edges which are vertex disjoint, which satisfy some nice properties about that matching. Because the underlying bipartite graph is complete, we have several matchings in that, and we would like to check which, or we would like to see which is a good matching according to our notion of goodness. And we'll take clues from what you had suggested earlier, right? So we will see that maybe we will try to assign students to their best top choice programs or universities. So let's try this. So that is A1 assigned to B2, it's top choice. A2 assigned to B3, A3 assigned to, so now B2 is gone, so B2 is not possible for this thing. We'll also check B3, B3 is also gone, therefore let's settle for B1, right? And A4 assigned to B4. So let's look at this assignment. So this is a valid assignment first of all, because every A has listed all B's, so you can potentially assign any A to any B, and it seems to be a reasonable thing to do because 3 out of the 4 people, 3/4 of the people have been assigned their top choice, and there is one person who is assigned his third choice, but we just live with that. So I would like you to stare at this assignment and tell me what are the good parts about it. One of them I have already said, and I have taken clue from your suggestion that try to assign as many people as possible to their first choice. And but if there are some drawbacks about this assignment, see whether you can identify them. Maybe there are some from the program side and so on. So each one of you spend some few seconds, think about it, and then let me know who has an answer. Yeah, we'll let everybody think and then take that. Yeah, from this row, if anybody wants to answer. Yeah, your row. The third one, if it helps. Yeah. Okay. So let's do the following. We will mark for every university. So B1 gets A3, right? Yeah, B1 gets A3, B2 gets A1, okay? Okay, yeah, and then let's do it for everybody. B3 gets A2 and B4 gets A4, which is again quite at a lower rank, right? Okay, so what should one do? So what is your proposed output? Universities should also be given some amount of priority, right? Okay, any other problem anybody finds? So this is in some sense a valid issue with this. We'll see whether we can address it all together. Yeah. Any other issue? Okay. Okay. Okay, so I'll take one point. So this is this you have made a good observation. I'll take one point from what she says is that currently there are two people who have B2 as their top choice, right? So even when there were two people, or in general, typically we expect that lot of people have the same choice, same kind of choice set. So one institute or one program is kind of very popular, and therefore it is going to be the top choice for many, if not for all. So if there are two people applying for the or having the same top choice, we are currently not looking at the universities or the programs preferences at all, but just looking at the students preferences, right? So, and in particular, let's look at a very particular case where we look at this A3 who is not assigned to his assigned to the her second choice, which is B3, and let's see what happens if A3 approaches B3, right? So A3 goes to the university and says that I would like to get I would have liked to get admission into your program. B3 says that the central authority or who has given this allotment has given me the student A2. So we look at B3's preference list and we see that A2 is a worse preferred student or worse ranked student according to B3's test or whatever examination or marks that B3 has given. So if you look at from B3's perspective, B3 is going to say that instead of taking A2, I would be happier taking A3, right? So this is a problem if you have multiple students who are assigned who are applying for the same program. We are not looking at the program's rank ordering at all. At the way we assigned this, we just went according to the student's preference, right? So while this assignment had this nice property that we had many students getting assigned to their top choices, we did not have the property that let's define it formally, that if you take any student program which is an unassigned pair, so let's make the definition formal. So we will call this assignment now from now on a matching. So while I'll not repeatedly say it, we have an underlying bipartite graph. In that, an assignment will now be called as a matching in the bipartite graph. A matching is only a collection of edges of the bipartite graph such that no two edges share an endpoint. So a matching is a collection of edges such that no two edges share an endpoint. So in our setup, there is a complete bipartite graph. So we will always be talking about matchings which match all the A's and all the B's. So these are these we will call as perfect matchings or perfect matchings. So every vertex is going to be matched in our matching. But we can also talk about edges. So for example, this edge A1, B2 in this matching is a matched edge. So I will use this notation to show this, that is an edge on which I have drawn a wiggly arrow is a matched edge. On the other hand, in the underlying bipartite graph, there is also this edge A1, B3 which is an unmatched edge, right? So what do I mean by unmatched edge? An edge along which the assignment has not been made. That is A1 is interested in B3, but we have not assigned A1 to B3. There can be another matching in which A1 gets assigned to B3. Right? So now we are given a bipartite graph. We have the preferences of the A side as well as the preferences of the B side, and we are interested in outputting matchings, and there are multiple matchings in this system because the underlying graph is complete bipartite graph. There are multiple matchings, but we are interested in matchings that satisfy some good properties according to the preferences of the participants, right? So as we were talking about, so this A3 B3 edge is an unmatched edge with respect to this matching because we have not made the assignment along A3 B3. And what we see is that A3 prefers its prefers B3 over its current partner. What is its current partner? What do I mean by this? So what is the current partner of A3? B1, because this is what is the assignment, that is what is it assigned to, current partner B1, and we also have that B3 prefers A3 over its current partner. What is B3's current partner? A2. How did we find this out? We found this out from the preference list of A3 and B3, right? And we compared the current partners with the respective ones, B3 in one case and A3 in another case. Now, if this happens, if you are aware, this can actually lead to a court case in such a system, right? Where A3 will approach the court and say that B3 had published this rank ordering and it did not go, the assignment was not made according to the rank ordering. In fact, I should have been assigned to B3 rather than this A2 being assigned, right? So in fact, let's ask, can A3 do the same thing for B2? So remember, A3 is assigned to its current partner, which is the third choice. So A3 went and approached B3 and it found that it could actually get assigned to B3. But why stop at its third choice? It can ask also, can I also get assigned to B2? Can I make a better court case where I can actually approach the court and say that I should have gotten assigned to B2? So let's see what happens when you look at this unmatched edge, which is A3 B2. So is it true that A3 prefers B2 over its current partner? That is true. Now let's ask the question for B2. So B2 is evaluating between A3 and A1. So we need to look at the preference list of B2 and check whether A1 is better preferred over A3. So what is the case? Yes or no? Yes. So in fact, not only that A3B3 is a problem, that is A3 can claim that it should have got assigned to B3, it could go ahead and say this for B2, right? So A3 does have a point to be unhappy about, and he will make a big case if such an assignment is output by the central authority, right? At the same time, you cannot expect that all the participants can get assigned to their top choice, because as we see, both A1 and A3 do have the same institute or program as their top choice, which is B2, right? So let us now say what according to us is a good matching. It may not necessarily satisfy all the criteria that you had specified, but it is a very well established and well accepted notion of optimality, and so all of us understand what is a matching. It is simply a collection of edges which are vertex disjoint or do not share an endpoint. Suppose we are given a matching M, that is an assignment in the system, that is we have a bipartite graph, we have preferences of both sides. We would like to ask whether this matching is good. We will say that a matching M or a pair AB is unstable or blocks M. So why do we use this term unstable? Because we see that A3B3 is a pair which is not happy with this assignment. So it is going to create instability by saying that I will throw away my current partner, that is A2, and get A3 assigned to me. Therefore, this is going to cause something which is not a stable thing, and this can go on forever, right? So this seems to be not a good situation. So AB is an unstable pair or blocks M. First of all, AB should not be a pair which is assigned in that matching. That is, in this picture, AB should not be an edge which has that wiggly thing on it. That is, it should not be an assigned edge, because otherwise it cannot block it. So we will say that in terms of notation, AB does not belong to M. That is, M is a collection of edges. So AB itself does not belong to M. Then we have two conditions, that is, A prefers B to its current partner in M, and it is conventional to denote this by M of A. So when I say M of A, it is its current partner in that matching. So if I call this the matching M, let's just make sure that we understand what is M of A2. What is M of A2? B3, because it is its assigned partner. M of A3 is B1. We can symmetrically say that M of B1 is equal to A3, right? So therefore this notation is common, that is, we will use M of A to denote its current partner in the matching. So A prefers B to its current partner and B prefers A to its current partner. In M, which is called as M of A. So in this case, it is called as M of B. Right? So if we are given this instance where both A's and B's have complete preferences, we look at this, and if we are given an assignment, we will look at every edge that is not assigned in this assignment and ask, is this pair a blocking pair, or is this an unstable pair with respect to this assignment? And this answer can be quickly obtained by looking at the preferences of the men and of the A's and the B's, right? Okay, so let's take some other pair. So maybe we will take A1 B4, right? So let's ask whether A1 B4 is blocking with respect to this assignment. So this is the edge A1 B4. Is it blocking with respect to this assignment? Yeah, maybe yes. What do you think? Yeah, behind you. No, behind you. Yeah. Yeah, that. Can you just ask? Yeah. Yes. Yeah. Okay, so why is it not a blocking pair? So it will be a blocking pair if it satisfies all these three conditions, right? So let's see whether it satisfies the condition that it does not belong to M. It indeed does not belong to M, so it's a candidate to be a blocking pair. Okay, then we will ask, does A1 prefer B4 to its current partner? No, this condition is not satisfied. From the B4 side, in fact, there is incentive for it to participate in a blocking pair because it is assigned to A4, which is rank 3 versus A1 is rank 2. So from B's side, it is indeed interested in switching to A1, but A1 is not interested in switching to B4 given its current partner, right? So this pair is not a blocking pair, whereas A3 B2 and A3 B3 were both blocking pairs with respect to this matching. Now quickly, can somebody say whether there can be any other blocking pair? So apart from A3 B2 and A3 B3, is there any other blocking pair with respect to this? Okay, why no? So the other three participants, A1, A2 and A4, have been assigned to their top choice. So they do not have any better partner to even think about getting or creating a blocking pair. So because they cannot participate, the only person from the A side that can participate is A3, and A3 has already participated in blocking pairs B2 and B3 with B2 and B3, right? So now we understand what is not a good assignment, because if you have blocking pairs, then these blocking pairs are going to create trouble either in terms of court cases or saying that these assignments are invalid and they are going to get assigned to each other. Therefore, having blocking pairs is not a good idea. So what we would like to have is, so we will say a matching M is stable if there does not exist any blocking pair with respect to M. So let's observe that a blocking pair can be defined only with respect to a given matching. So if I am given just this preference system, then I cannot define what is a blocking pair. Unless I am given a matching, some candidate matching to begin with, I cannot talk about what is a blocking pair. So what my goal is to be able to output a matching which we will call as a stable matching, and this matching is a matching in which if you look at any unmatched edge, that is what we have drawn here, the edges which do not have these wiggly lines, these do not form blocking pairs, or their endpoints would not at least one of the endpoints is not interested in switching to the other. If both the endpoints are interested in switching to each other, then that pair blocks that matching or is an unstable pair with respect to that matching. So the question that we would like to ask is, now these preferences are governed by participants who are individuals who have their own preferences. These rankings come out of a system where exams are conducted. So there may be arbitrary preferences of both the students as well as the institutes. Now given any system, arbitrary system where I have n students and n programs and a complete bipartite graph with 2 ranks on each of the edges, can I output a matching which has this property, which is a stable matching, right? So does there exist a stable matching, and if it exists, can I find it efficiently by some algorithm or procedure, right? This is our goal. Is the question clear? Are there any questions about the system or in the model? Okay, and in fact this problem while it was studied in 1962 as the college admissions problem only, this has a little more historical this thing to it. It was indeed used in something called as the National Residency Matching Program in the US, where these A's are interns and B's are medical interns, doctors who want to do their internship, and these B's are hospitals, where again each hospital, like the earlier college admission, has capacity and would like to take multiple interns. But again there was a preference system on the interns as well as the hospitals. So, but when we study it in this one-to-one setting, that is both the A side as well as the B side is having unit capacity, that is they just want to get one partner from the other side. This very naturally is called a marriage model, and therefore this problem is called the stable marriage problem. So from now on, instead of calling these as interns or hospitals or students and this thing, we'll call the A side as men, which is customary in the literature, and the B side as women, right? And like in the marriage, you want to get just one partner, so therefore this very naturally fits the marriage model. So therefore you have this this thing where you have each one of them having unit capacities. So we will call them as men and women from now on. So the A's will always be called as men, the B's will be called as women. So now is everybody okay with the definition of what is a stable matching? It's also called as a stable marriage or a stable matching. So what I would like you to spend some time and find out is there an assignment which satisfies this nice property? That is, if I look at any unmatched edge, then indeed it does not block that matching, right? So this matching is not stable. So M is not stable. If a matching is not stable, we can quickly show a blocking pair. Even if you show one blocking pair, that is a witness to show that it is not a stable matching, right? So if I want to verify that a matching is whether a matching is stable, I can simply go over the unmatched edges, ask each one of them, are you a blocking pair? If the answer is yes for any one of them, the matching is not stable, else the matching is stable, right? So therefore, please spend some time and find out whether this system has any stable matching. That is, can you fix the partners of A's and B's such that no unassigned pair or unmatched pair blocks that matching?